polynomials anyways, so this is just fantastic. Alright. Okay. Hi. We're having technology issues anyway, so that's a good thing, really. Okay. So we are graphing polynomial functions. They're not going to be a general form. They're just going to be like in any random form. So sometimes they'll be an intercept form, which will be nice because it'll give you points. Other times you'll have to factor it to actually get an intercept form, which we're really good at because we've done such like division for weeks. It feels like. Yeah. Okay. So we know polynomial functions, they're going to be any graph, basically. It's just as long as there's a smooth curve, it could be any curvy, wonky thing that you could do. Okay? So the turning points, if you're given a polynomial with degree n, the number of turning points is less than or equal to n minus 1. Right, so if we had like a cubic polynomial, the degree is 3, so I could have a total of 2 turning points. So it changes from increasing to decreasing, or it could have 1 or it could have 0. Okay? Parabola, it's to the second power, so has n minus 1 turning point basically. Fourth power could have 3, and so on and so forth. So this is just kind of nice to know. There's no specific way to actually find these turning points unless it's a parabola. Then we have the vertex formula. But every other turning point, we have no way to like know it up front unless we're just plotting what can happen on it. Which sometimes happens. Okay. So we all know zeros are like the x-intercepts, right? So zeros could be x-intercepts. I've sometimes called them factors. I've heard them called roots before. So they're all like representing the same thing. Different words to represent the same thing. That's how mathematicians do things, just to make it complicated. So, let's just say we have a 0 of, I don't know, A. I was going to lose it. Woo! So, first case, if my 0 is to the first power, basically, graphically wise, this is intersecting the x-axis. So if I was graphing the 0, it would go straight through it. Nothing too crazy. So here, I'll even draw a picture. My 0 is right there. It's going to go. Woo. Option number 2. You have x minus a to the second power. Then it's a turning point on the x-axis. So same thing, if my x-intercept's right there, it'll go and turn right back around. And it could be above it. Doesn't have to be a parabola either. And my last option, x minus a to the third power. So I'm going to say it looks like a cubic at the x-axis. So this one was weird. I actually didn't know this until I have this textbook, so it's interesting. So at this x-intercept, it basically goes, flattens a little bit and goes back up. I didn't know that. That's interesting. I don't know what happens if it's a fourth power. I'm assuming it's probably a turning point. Again, if it's a fifth power, it'll definitely be intersected. I don't know what it would look like. But even powers will turn around. Odd powers will go straight through. Depends on what it would look like, though. So yeah. We have two examples that we're going to graph. So the first option, we have it in factored form. So the goal is to basically plot all the x-intercepts and find the y-intercepts and plot some points to just do a smooth curve type of situation. And we can use our end behavior from yesterday. So I guess if I was doing this, I'd figure out the degree and leave coefficient so I know the end behavior. Especially this one, it looks kind of weird, so I can't pick out the degree. Just by like seeing it, I guess. So what is the degree of the entire shebang? Yeah. So it should be a degree of 4. I have this exponent of 2, x minus 3 to the first power, x minus 1 to the first power. If I add all these degrees together, I get a 4th degree polynomial. Basically, if you distribute it out, you get x to the 4th eventually. And then what is my leading coefficient? I don't know, whatever I used yesterday. Okay. Yeah, which is in front of this parenthesis thing, so -1. So the end behavior, where would my arrows be pointing? Yeah, they're both, yeah, it's even degrees, so the arrows are going in the same direction. It's negative, both arrows are pointing down. So it could have as many turning points in the middle. Okay. So now that I know kind of the shape of it, I can find the x-intercepts. Which are what? Yeah. So this is in factored form. I could set each part equal to 0 and solve. So 1 and 3, those would be intersecting through the x-axis. At 2, what's happening? Or -2. Yeah, it's a turning point. Okay. So I'm just going to start plotting this, and then we're going to make a table and plot some points to finish it. So that's 1, 3, -2. Okay, so the directions, we have it in factored form. We have plotted the x-intercepts. We should find the y-intercepts. How would I find the y-intercept? Yeah, plug it in 0 for x. So f of 0 equals -1, -3, then 2 squared. And then multiplying all this together. Well, that's just nasty. Yeah. Okay. So -12 would be like way down here. Close enough. Okay. I would probably plot a couple more points. Just looking at it, I kind of have a general idea of what's happening. We know that -2 is a turning point, so either it's going to be like relative there or up. I'm assuming it's going to be down since my end behavior is down, and I have this y-intercept down here. That's my conjecture. But you plot -1 just to make sure it could be -3 if you wanted to. But I mean, pretty confident it's going to be turning around this way. We'll go back down and come back up. The only question I'm concerned is how high up does it go up to? So I know where to turn around and go back down. So I plug in 2 to the x value and simplify. That's 16. You plugged into. Okay, so way up there. So going up, hitting 16, coming back down. Yeah. I mean, I'm okay with a rough sketch like this because I don't like to graph. I'm kind of lazy. If you wanted to count by twos on the y-axis, you would. But we know we just connect everything with the tooth first, connect all the dots where you want to, right? Seeing them all. You can always check it. You can type it into desmos.com, so it looks like. If you want to do it that way. Good with this one? Okay. Here's our next one. So unfortunately, it's not in factored form. They will ask you to write it in factored form. So we're going to have to do that. We can figure out the degree and the coefficient first so we know the shape of the end behavior of the graph. So what's the degree? 3. The coefficient is. Yeah. So then what's the direction of my arrows? Yeah. Left is falling, right is rising. Basically, odd is either increasing or decreasing. So it's a the coefficient positive, it has to be increasing. I could have 2 turning points or 1 turning point or 0 turning points for the cubic. Writing in factored form is going to be interesting. Unfortunately, we can't just cut it in half and factor by grouping. That'd be kind of nice. So give us some stuff, but we're going to do rational zeros test. Find one that works and factor it. So I did the whole P over Q thing. What are my P values? Or what does P represent? Yeah. The 6, then you do what's all factors of 6? Yeah. And the Q would be 2. Yeah. So then I could test all of these different numbers, figure out which one works. One works. So we can do synthetic division with 1. So we have 2, 5, 1, 6. Okay. Doing synthetic division, this is what we get out. How would I write f of x in factored form so far? Okay. And then I could write the linear factor with it. How would I find using rational zero test? Yep. So this guy, we're going to have to do AC method. Sadly. So it's going to be 3. But now, factor out with the column. So this AC method, x minus 1 would carry down. This is f of x in factored form. Okay, so that should have been a review of what we did last week. Okay. What are the x-intercepts of my graph? Okay. So you can set each parenthesis basically So x-intercepts, what about the y-intercept? We plug in 0 for x, so I can either plug it into the factored form. Yeah, I would plug it into the original, because then the first three terms are all 0, and then it's just 0 minus x, which is negative 6. Makes it a little easier. So I'm going to plot all these points. And then see if we have to fill in gaps. Okay. What is the behavior at the x-intercept? So are we intercepting, turning around, or is it like a cubic situation? Yeah, so they're all intersecting 0. And then I know the end behavior, I have to be increasing. So at my left node 0, that should be falling. So I should be decreasing on the left side. My right node 0, I should be increasing on this side. So I like plugged in the end behavior. I know it'll have to be a smooth curve connecting all this stuff. I don't know if I'm feeling too ambitious that I plug in a point between -2 and -3 marks, because that is -1.75. You could if you wanted to, or you can just go up a little bit and then go back down. Then down your y-intercept and then back up. Yeah, just so make like a horizontal line between -2 and -3 halves. I've seen people do that before, where they think you just go up and then straight across and go back. We don't have like flat lines in polynomial graphs. Okay. Sounds good.
Can I go to Mrs. Benton's and finish the lab?
Yes.
Thank you.
Yeah.
You all write the assignment down.